Oh, hi. Yeah, this is Tong Zhang, the chief scientist at SkillFlux. It is really my great honor to have this opportunity to share our research on rethinking the implementation of B-tree upon the arrival of a computational storage drive. So the title of the talk is Computational Storage Drive, making the best data structure B-tree even better. Okay, so with a very kind of a humble start over 15 years ago, SSD or solid state drive has come a long way and made amazing progress. So today, the solid state drive has become one of the cornerstones of modern computing infrastructure. So in current record SSD 1.0 era, the goal is to unleash the full potential of NAND flash memory and continue to deliver faster and cheaper solid state drive products. So as a SSD controller technology is quickly becoming mature, the difference between SSD products are getting smaller and smaller. So we are currently at the end of SSD 1.0 era, and at the same time, with the slowdown of Moore's law, heterogeneous computing has become inevitable. So driven this trend, the era of SSD 2.0 was born naturally. Its goal is to provide meaningful data processing capabilities in addition to maintaining the cost-effective storage functions to better serve future heterogeneous computing systems. So this will naturally introduce a deeper coupling between the software system and the SSD hardware, presenting a huge space for system design optimization. And today is still the beginning of and the exploration stage of the SSD 2.0 era. So based on our experience and the lessons in the past few years, we will share some of our thoughts on this new paradigm and present a successful case study on innovating B-tree implementation in this SSD 2.0. So really the idea of pushing certain computing tasks down into the storage has a beautifully simple rationale. The moving computation closer to where data locate could improve the system performance, reduce power, and reduce the cost. Intuitively, this simple rationale makes a perfect sense and almost impossible to refute. However, up to now, its large-scale commercial success has remained almost completely missing. And despite amazing results on papers and hundreds of millions of dollars spent on R&D. So this shows that the commercialization of SSD 2.0 is far more challenging than what the academia and the industry have expected. One fundamental challenge is how SSD 2.0 could fit into the existing software ecosystem in the most natural and non-disruptive way. So in their legendary computer architecture textbook, Professors Patterson and Hennessy list 8 great ideas in computer architecture, where the abstraction ranks the second. Indeed, abstraction is a key design principle underlying modern computing systems. Without the abstraction-centric design philosophy, today's information technology ecosystem will simply not exist. But unfortunately, heterogeneous computing by nature break away from the principle of abstractions. Of course, it is true for all the heterogeneous computing solutions, not only SSD 2.0. As a result, all the heterogeneous computing solutions must pay the cost of breaking the abstractions in the existing systems. For example, the cost of modifying the software at one or multiple abstraction layers and modifying the interface and the APIs across adjacent layers. Clearly, whether a heterogeneous computing solution is commercially viable depends on whether it has a justifiable and favorable cost versus benefit trade-off. The success of devices like a GPU and a smart NIC essentially attribute to their justifiable cost versus benefit trade-off. Now let's look at SSD 2.0. So located at the very bottom of the entire storage I/O stack, connected through standard cross-layer interface, SSD 2.0 clearly faces a higher, much higher abstraction breaking cost than the others. So we firmly believe that in order for SSD 2.0 to take a real first step towards the commercial success, we must move away from the traditional computing offloading mentality. Therefore, we have to look into we call the native in-storage computation that is transparent to all the other abstraction layers. The transparent in-storage computation should have two properties. One is a wide applicability, and two, low efficiency of CPU-based implementation. So intuitively, the general purpose lossless data compression is a very good candidate here. Besides its very wide applicability, lossless data compression is dominated by random data access that causes very high CPU cache miss rate, leading to a very low CPU hardware utilization efficiency. So the basic structure of SSD 2.0 with built-in transparent compression is very simple. The data compression and decompression are carried out by the hardware on each 4K byte block along the I/O path, which is completely transparent to the upper level operating system and applications. It is simply deployed as a standard NVMe SSD. The software stack, including block layer file system and the user applications, do not need to be modified. So it is very easy to achieve a favorable benefit versus cost trade-off. Now let's look deeper into the benefit. To most people, transparent in-storage transparent compression just means transparently reducing storage cost and transparently improving IOPS, nothing else. Initially, it was also what we thought. However, as we carried out further research, we more and more realized that it is far from the complete picture. Beyond the obvious benefits as listed here, transparent compression actually opens a door to very exciting innovations that, however, remains largely unexplored. The more we could exploit such a hidden potential, the more we could establish a favorable cost versus benefit trade-off to justify the commercial value of SSD 2.0. So first, we know that all software, actually all the software architecture design is essentially a compromise considering the trade-off among multiple factors, of course, including the storage cost. So when we upgrade from SSD 1.0 to SSD 2.0 with built-in transparent compression, as long as data has sufficient compressibility, the storage cost will become much less important. This will accordingly expand or increase the software architecture design space, which will enable much more innovation opportunities. So in particular, with the in-storage transparent compression, we no longer have to fill each 4K byte block with valid user data because any unoccupied space will be simply compressed away inside the storage device. So as a result, we could pack any arbitrary amount of valid data, for example, 2K byte, 1K byte, or even 100 byte within each 4K byte I/O block. So this leads to a virtually variable size block I/O. That is, even though we still stick with the conventional 4K byte I/O interface, the valid user data per block could have a variable or arbitrary size without sacrificing the true physical storage space. This could bring a unique opportunities to rethink the design and implementation of a data management software to gain various benefits such as higher performance and a lower implementation cost. So really in this context, all the innovations and the modifications are confined entirely within the application itself, where the existing interface across the entire abstraction layers remain completely unchanged. Clearly, it is highly desirable to the end user, and there is a much less concern on hardware vendor lock-in. Therefore, we only need to make sure that the cost of modifying applications can be justified by the gain benefit. So based on how much we need to modify the applications, we may categorize the entire design space into 3 stages, as shown here. So in the remainder of this talk, I will use an example in the stage 2 to showcase the exciting innovation potential here. So the example here is about the reducing the B tree write amplification, or like to make the B tree even better. We all know that today B tree faced a strong competition from another indexing data structure called a log structure merge tree because of these 2 widely cited advantages of the log structure merge tree, including the less storage space usage and a much smaller write amplification. Once we run B trees on storage drive or SSD 2.0 with transparent compression, the storage space usage advantage of log structure merge tree will largely disappear. And moreover, by leveraging the virtually variable size block I/O, we may reduce the B tree write amplification through the a very simple idea called page modification logging. For example, as shown here, associated with each 8K byte B tree page, we assign 4K byte logical storage space for modification deltas. It is a very simple idea, but it is not practically feasible if B tree runs on normal conventional storage drives. Once we modify the B tree and it runs on SSD 2.0 with transparent compression, we can significantly reduce the B tree write amplification and make all the advantages of the log structure merge tree largely go away. So that is the reason why we claim that here we make the best data structure B tree even better. So to further illustrate, let's consider this following example. So for each 8K byte page on storage, we allocate the 4K byte block to store its modification logs and initialized at all 0. This 8K byte page has been loaded into the host memory, and suppose we modify a small segment in the 8K byte in memory. Later, we need to evict this page from the memory. Instead of flushing the entire 8K page from the memory to SSD, we create we create an in-memory all 0 4K byte block and copy the modified segment into it. Then through the normal 4K byte I/O interface, we write this mostly 0 4K byte to the SSD 2.0 as shown here. And finally, we evict the 8K byte page from the host memory. Later on, we reload this 8K byte from the SSD by consolidating the original page with the delta. And again, we modify one more segment in the 8K byte page. Then to evict this page from the memory, we create an in-memory all 0 4K byte block and copy both segments into it. through the normal 4K byte in I/O interface, we use this new 4K byte block to overwrite the existing one on the storage device. And finally, we evict this 8K byte from the memory. In the exactly same way, we again reload the 8K byte page from the storage and do another modification. And to evict this page, we create another 4K byte block in memory and hold all the three segments and overwrite the existing one on the storage device. And finally, evict the 8K byte page from the host memory. So in this way, to serve 3 30-page evictions instead of writing 24 kilobyte as in conventional practice, we leverage the SSD 2.0 with the in-storage transparent compression to invoke no more than 4K byte writes to the physical storage media without any change to the interface between the host CPU and the storage device. So for the purpose of demonstration, we have implemented a so-called B- tree by incorporating this simple design approach into a normal B tree and then compared it with RocksDB that use a log structure merge tree and the MongoDB that use a normal B tree. The results here show that compared with the log structure merge tree, normal B tree indeed suffers from at least 4 or 5 times higher write amplification. With a modified B tree or B- tree, we can dramatically reduce its write amplification and even less than that of log structure merge tree. Therefore, once we appropriately modify B tree by leveraging the SSD 2.0 with the computation capability, that is transparent compression, both advantages of log structure merge tree will be gone. And as a result, compared with the B tree, the log structure merge tree becomes much, much less appealing in practice. So this will make the widely used B tree become truly the best indexing data structure. So this is just one example to showcase the innovation potential. And we have been exploring how to rethink the implementation of many other data management functions, such as a hash-based key value store, caching, snapshot, and RAID in this era of SSD 2.0 with built-in transparent compression. So certainly to clarify that I'm not saying that the SSD 2.0 is only about integrating transparent compression capability into SSD. We believe that transparent compression is the best way to start this exciting era of SSD 2.0. And we, of course, have a long way to go to unleash the full potential. And there are many challenges and innovation potentials along the way. So at ScaleFlux, we sincerely look forward to working with the research community and the industry to explore this very exciting journey. So this ends my talk. Thank you very much.